Hey, AP Chemisters, this is Mrs. Vanderwall bringing you the Chapter 10 edition of the Blank Wall series. Chapter 10 is a continuation of the chemical bonding chapter, and in this one we talk about molecular shapes. And this is a very important section. They do talk about this in the AP, especially during your some of your multiple choice could have this, or your free response could have this. You might recall these basic shapes when you took first year chemistry way back when, and we use something called the VSEPR theory, which is the valence shell electron pair repulsion theory. This is where we talked about a linear, bent, trigonal, pyramidal, octahedral, those terms, those shapes. So we're going to revisit those. Please know these. Please commit them to memory. You will need to know those. So why do we even care about geometry? Structure will determine function. We will talk about why some molecules are polar and nonpolar in this chapter, because the shape will depend on that. If it's completely symmetrical, then it is a nonpolar molecule. It makes no difference what the bonds are. The molecule itself would be nonpolar. If it's asymmetrical, where you have like an oxygen not being pulled equally on either side, then you're going to have a polar molecule, which will then determine the function, like it will dissolve in water or it won't dissolve in a nonpolar substance. So this is what this chapter is going to be all about. VSEPR, again, I already told you, is the valence shell electron pair repulsion theory. The key term here is repulsion. You know that the electrons will repel each other. The idea behind VSEPR and shape is that the preferred geometry right here of the molecule is one in which electron groups have the maximum separation as possible. Why is that so important? Because the maximum separation means lowest energy. Do you remember Coulomb's law? Energy equals K Q1 Q2 over R. We talked about this when we talked about lattice energy, when we talked about the ionic compounds and the bonds. We talk about this here as well, because if you have these like charges, these electrons, you know that they're going to repel each other. So if they have like charges, the potential energy is positive, and it will decrease the particles as they get further apart. Why? Because look at this term right here, because of the R. With R in the denominator, a larger R will decrease that whole amount and the energy decreases. So the maximum separation means lowest energy, greater stability. So in 3 dimensions, how far apart can these electrons get away as far apart as they can from each other? So let's start with the beginning, the real basic, and that would be a linear group. So it says draw the Lewis diagram for beryllium chloride here. Beryllium, you might think, well, golly, that's a metal, so why would I even draw the Lewis structure for that? Do I have to show it as an ionic compound? And actually it has the covalent tendency. So I will start off with beryllium, and it has 2 valence shell electrons. Here's your chlorine with its 7. And there we have it. So how far apart can those 2 chlorines be from one another? And it ends up being 180 degrees. Okay, so 2 electron groups, that would be, these guys right here, are as far apart as they can be at 180 degrees. Maximum separation for really anything. So that would be beryllium chloride. What about the next one for carbon dioxide? Well, I won't go through how I got this. We've done carbon dioxide so many times, I'm sure that this looks familiar. But once again, how many electron groups are on the carbon? 1, 2. What's an electron group? I think I may have skipped over that. Whoops, electron group, let me scroll it up a little bit, is either a lone pair, a single bond, or multiple bonds. So it's how, here we have the single bonds. That's electron group, this electron group. Here I have multiple bonds and carbon dioxide. Let me scroll this one down a little bit. And so this is still an electron group, and this is still electron group. It can be, again, a lone pair. We haven't seen that yet. So how many electron groups does carbon have on it? And it's just 2. So what is its geometry? Once again, it's linear. How far apart can those 2 electron groups be? So what about 3 electron groups, trigonal planar? Boron is what's called a metalloid, as you might remember. It does take on the covalent character, so I'll draw the Lewis diagram. It has only 3 valence electrons, so I'll put my fluorines around it. And fluorine up here. And how many electron groups does this boron trifluoride have? 1, 2, 3. So it has 3 electron groups. So how far apart in 3 dimensions can 3 electron groups get? 120 degrees. So what is that shape? It is trigonal planar. So you probably can see the triangle going on right here, and it's in one plane. You might remember your geometry like we did for the linear, 2 points determine a line, 3 points determine a plane. So it's trigonal planar. You have 3 electron groups, trigonal planar. So let's try this next one, COH2. Okay, whoops, hang on a second, I think I went down too far. Here we go. So what's my central atom? It's carbon. And if you just believe me here, I'm going to do this. There we go. And so that would be your COH2. How many electron groups does this have? It has 1, 2, 3. Again, don't worry the fact that this is a multiple bond here, a double bond. It still is considered an electron group. So it still has 3. And what would be its geometry? Well, if it's 3, it's trigonal planar. Okay. These are your basic shapes. We're going to go into particulars if I have some lone pairs. Notice that so far none of these have lone pairs. And I'm just showing you the basic shapes. Sorry, my board is, you know how much I love my board. So 4 electron groups is tetrahedral. Do you remember what the prefix tetra means? We've used that before. Tetra means 4. Hedral means sides. So tetrahedral is a 4-sided figure. So draw the Lewis diagram for CH4. I hope you remember this. Now, when I draw it like that, looks like it's a square. It looks like it's smashed on a piece of paper. But remember, we're talking 3 dimensions. So how far apart can 4 things in 3-dimensional geometry be as far apart as they can from each other? And it ends up being 109.5 degrees. That is the maximum separation in 3 dimensions. So really, when I draw it like this, it kind of gives you a false impression on what this structure really looks like. So a tetrahedral is a 4 electron groups 109.5 degrees apart. Let's draw a silicon tetrafluoride. It's going to look very familiar, and I'm going to kind of give it a little bit of a 3-dimensional feel. Notice how I didn't make these perfectly straight out. Try to make it a little bit bent there. How many electron groups does it have? Well, if you count 1, 2, 3, 4, it has 4 electron groups. Its geometry, again, is tetrahedral. So 4 tetrahedral. All right, let's try the next one. I love my board here. 5 electron groups. Okay, I always thought 5 was kind of a fun, because you do some fun shapes with this one. So phosphorus pentachloride. You may say, now, wait a minute, how can phosphorus have 5 bonds? You can't do that and still fulfill the octet rule. And again, that is correct. Let me just kind of show you something real quick. If I'm going to show you, here's my S, here's my P for phosphorus. So if I show my orbital notation for phosphorus, there it is. But how many bonding sites do I have? I have 1, 2, 3. Golly, I need 5 bonding sites because I have 5 chlorines. Where does that next bonding site come from? Well, it just so happens phosphorus is in the 3rd energy shell. And if you remember Schrodinger's equation way back in chapter 7, we know that there is a 3d orbital out there. It exists. It's empty right now, but it exists. So what happens is that this electron will get promoted into the D shell. And what happens, we now have, if I erase this one, 1, 2, 3, 4, 5 available spots to bond. So phosphorus can be an exception to the octet rule. So if you're getting into the third energy shells, your 4 energy shells, so sulfur could do this, bromine can do this, chlorine can do this. However, carbon, nitrogen, oxygen, fluorine cannot. So having said this, it's why phosphorus can disobey the octet rule. Let's go ahead and draw this. So I have phosphorus, and I have the 5, and I'll put the 5 chlorines in it, and there we go. Okay, and so what shape does this have? Well, maybe if you look at this picture right here, you'll really see that this is 180 degrees up and down, and then you have a triangle in the middle. So if you have that shape, watch, you have up, 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 you have a triangle pyramid in the top half, and you have a triangle pyramid in the bottom half, and then we call this trigonal bipyramidal. So what is that really saying? That I have 2 pyramids with a triangular base. So it's trigonal bipyramidal. This should be trigonal bipyramidal. Please fix that for me, because trigonal pyramidal is another shape. Okay, so there are 5 electron groups. Did you fix that? Did you fix that? We have 120 degrees apart. That's when it's in the triangle area, and then it's 90 here and here. Okay, 6 electron groups. Let me go on. Here you go. Again, sulfur. Remember what we did with phosphorus? Let's do sulfur again. Oh, my board. I love my board. Okay, so right now when I did the orbital notation for sulfur, look what happens. I only have 2 bonding sites. Well, I need 6 bonding sites for the 6 fluorines. So if you look on your periodic table, you're going to notice that it's in the 3D, or it's in the 3rd shell. So I can get the 3D orbital going. Let me promote one of these. I love my board. And now I have 4 open spots. So let me promote this one, and now I have 6 open spots. So if I were to go ahead and sketch this out, I have 6 available locations. There is my Lewis diagram, and how far apart can I put everything? Everything is 90 degrees. Here's like a square in the middle, up and down. So you might say, oh, is that going to be square bipyramidal? And not quite. We call it octahedral. So if you count the 4 sides on the top, and the 4 sides on the bottom, total of 8 sides is octahedral. So you have 6 electron groups are 90 degrees apart. Why don't you go ahead and in problem number 1, draw those, pause this, do problem number 1, and then come back and see how you did. All right, so 2 electron groups, remember 2 points at terminal line. 3 electron groups, remember 3 points are going to be coplanar. 3 points terminal plane, trigonal planar. 4 electron groups is tetrahedral. 5 electron groups, what I do is I draw a line and then kind of draw your triangle in the middle. And then 6 electron groups, here are my 4, and then whoa, up and down. I love my board. Let's see if I can't do that. That's better. So there are your 6 shapes. So, or excuse me, 5 shapes. So remember, we have linear, we have trigonal planar, are you writing this down? Tetrahedral, trigonal bipyramidal, and octahedral. Okay, problem number 2, go ahead and sketch or do problem 2. Pause this board here or pause your recording and then see how you do. All right, so hopefully you got these Lewis shapes. Letter A. How many electron groups does this have? I see 1 electron group, 2 electron groups, 2. So 2 electron groups equals linear. Okay, here I have 1, 2, 3 electron groups. So it is trigonal planar. And here I have 4 electron groups. So it's tetrahedral. Now, in the case of the nitrate ion, there is a resonance here. You could put your double bond on the top or on the left or on the right. That doesn't make any difference to the shape. That's it for 10.2. Stay tuned for 10.3.